Astronomers tracking 3I High Atlas report behavior that should not exist. Its chemistry is inverted, its acceleration ignores gravitational math, and its geometry pulses like a thermal heartbeat. The chance of even one of these anomalies is vanishingly small. Yet here, all three converge in a single interstellar body, cutting through our solar system right now. And this is not the first time. Oumuamua broke the rules in 2017, Borisov bent them in 2019. Now Atlas arrives. Stranger still. And if these anomalies hold, they don't just challenge comet science. They challenge how we defend our planet and what it means to be a bystander in the solar system. Coincidence or choreography? Accident of nature or something engineered? Three-eyed Atlas first appeared in the automated scans of Pan-stars in Hawaii Sea, flagged by its unusual path and logged within hours by the Minor Planet Center. Its orbit was quickly confirmed to be hyperbolic, the mathematical signature of an object not bound to the sun. Instead of circling back like comets of local origin, Atlas is cutting straight through the solar system, a messenger from deep interstellar space. This makes it only the third such visitor ever recorded. The first, 1I Oumuamua, stunned astronomers in 2017 with its cigar-like shape and unexplained acceleration. The second, 2I Borisov, discovered in 2019, behaved more like a conventional comet, yet carried a volatile richness unseen in most local bodies. Each arrival was supposed to be a once-in-a-generation anomaly. Now, just years later, the third has arrived, already challenging assumptions about what interstellar debris should look like. NASA's Jet Propulsion Laboratory and the Harvard-Smithsonian Center for Astrophysics both confirmed the early tracking data, but with a caveat. Atlas's motion deviated slightly from the clean gravitational arc predicted by initial models. The difference was small at first, but persistent, enough to trigger follow-up from the Very Large Telescope in Chile and ground-based radar networks. That persistence drew attention. In orbital mechanics, tiny residuals matter. When an object ignores gravity's script, even by a fraction, the reasons demand explanation. Atlas was already riding its own trajectory. The first real shock came not from the orbit, but from the light. Early spectroscopy performed by Pan-stars hinted that Atlas was shedding more carbon dioxide than water. That inversion, CO2 dominating instead of H2O, was confirmed in August by the James Webb Space Telescope and the Very Large Telescope's UV spectrograph. The numbers were stark. Early estimates suggested CO2 production nearly 20 times higher than water vapor. In comets of the inner solar system, the ratio is almost always reversed, with water vastly outgassing carbon dioxide. Such an inversion has never been confirmed in a bright comet before. The anomaly deepened as spectra accumulated. Atomic nickel lines appeared strong and clear, venting steadily from the coma. But the usual partner element, iron, was far weaker than expected, falling below detection thresholds in multiple measurements. In nearly all comets studied, nickel and iron appeared together. Here, nickel seemed to stand almost alone. The statistical odds of seeing both anomalies, CO2 inversion and nickel without iron, are so low that the International Astronomical Union flagged Atlas as chemically peculiar in its preliminary circulars. Some researchers suggest a natural cause, perhaps a unique stellar nursery where CO2-rich ices condensed, or billions of years of cosmic ray weathering that selectively stripped more volatile compounds. Others raise bolder hypotheses, still carefully labeled as speculative. Could selective absence indicate not just an accident of chemistry, but some engineered filtration in its history? For now, no model accounts cleanly for all the data. Atlas's chemical fingerprint is not just odd, it is a puzzle piece that does not fit the frame. By September, attention shifted from chemistry to motion. Precise tracking showed that Atlas was not traveling on a pure gravitational arc. A residual acceleration, subtle but measurable, pushed it off course. The effect could not be explained by the visible outgassing of its tail, which appeared too weak and misaligned to account for the thrust. Harvard's astrophysics team compared the anomaly to 1I Oumuamua, which in 2017 also exhibited a non-gravitational acceleration without clear cometary activity. Atlas seemed to echo that mystery, but with a visible coma that should have resolved the question, except it did not. Outgassing vectors and acceleration vectors simply refused to match. Rotation studies complicated the picture further. Light curve analysis suggested Atlas was not spinning in a simple principal axis rotation. Instead, its brightness modulated slowly, consistent with a tumbling nucleus or a near-spherical body rotating irregularly. Astronomers began describing it as a slow thermal heartbeat, as though periodic pulses of energy were driving its geometry in ways unseen in typical comets. That left the statistics. 3 interstellar visitors have ever been recorded. Each carries anomalies. One accelerates without gas, another is chemically overloaded, and now Atlas fuses both traits. The chances of all 3 being strange outliers by coincidence are vanishingly small. Is the solar system simply unlucky? Or has it stumbled into a sequence that hints at something deeper, something choreographed? For now, Atlas spins, accelerates, and refuses to obey the rules. As Atlas approached the inner solar system, the timing created a problem. Its trajectory carried it into a solar conjunction, slipping behind the sun from Earth's perspective. For weeks, ground-based observatories would be blind to its activity. This blackout window left astronomers uneasy. Outbursts or sudden changes in trajectory could unfold unseen, hidden in the glare of the sun. To mitigate the gap, monitoring shifted to solar instruments. The Parker Solar Probe and SOHO, both tuned to study the solar wind, were repurposed as watchers of opportunity. Their coronagraphs could glimpse fragments of Atlas's activity, but not with the resolution needed to track subtle shifts. The loss echoed past frustrations. Several bright comets have been swallowed in perihelion windows, their final stages never witnessed. Some disintegrated completely, others re-emerged in altered form, trajectories rewritten by forces unseen. Atlas now entered that same curtain of uncertainty. In planetary defense circles, the worry was not impact risk but interpretation. If the anomalous acceleration persisted or worsened, weeks of lost data would erase the chance to pinpoint causes. What came out on the other side, if Atlas survived, would either confirm the puzzle or deepen it. Astronomers braced for a reveal. Behind the scenes, the data was already circulating. Internal memos from NASA's Planetary Defense Coordination Office flagged Atlas as an object of interest, with updates routed to the Near-Earth Object Observations Program. The concern was not collision, projections showed no risk, but anomaly. An interstellar body behaving outside established comet models demanded scrutiny. At Harvard, the Smithsonian Center for Astrophysics hosted a series of discussions. The central question: could Atlas's non-gravitational acceleration be explained by radiation-driven sublimation, or was another mechanism required? Papers drafted during the blackout window proposed exotic but still natural causes, such as uneven CO2 venting across fractured surfaces or delayed release from deep subsurface pockets. Yet alternative hypotheses crept in. In one seminar, researchers noted the nickel without iron signature as suggestive of selective processes unlikely to arise randomly. The phrase "built, not born" appeared in notes, not as a conclusion but as a deliberately provocative frame for discussion. Officially, all such ideas were labeled speculative, bracketed as possibilities rather than statements. NASA's public statements remained conservative, emphasizing observation and data calibration. But privately, teams prepared for surprises. If Atlas re-emerged with its anomalies intact, it would sharpen the divide between conventional models and the growing suspicion that something more than coincidence was at work. Every discussion of Atlas circled back to its predecessors. In 2017, the first interstellar visitor, Oumuamua, passed within 0.25 AU of Earth. It showed no coma, no dust, yet accelerated slightly as though propelled. Explanations ranged from hydrogen ice sublimation to fractal dust sheets, but none resolved the evidence completely. 2 years later, 2I Borisov appeared, unmistakably cometary. Its outgassing matched solar system chemistry, yet in abnormal concentrations, especially cyanide and carbon compounds. Unlike Oumuamua, it looked familiar, but its composition exceeded normal bounds. Now Atlas had arrived, blending traits from both. Like Oumuamua, it accelerated in defiance of gravitational math. Like Borisov, it displayed a coma, but with chemistry inverted, water suppressed, and carbon dioxide dominant. Added to this was the nickel signature without iron, a rarity even in deep catalogs. Statistically, the alignment was difficult to ignore. 3 interstellar visitors, 3 anomalies, all within less than a decade. Models predicted such visitors would appear once every 50,000 years on average per star system. To see 3 in such quick succession was rare enough. To see each exhibit unexplained features made the odds vanishingly small. The debate polarized. Coincidence, said one camp. Our detection tools are better, and anomalies are simply what we notice first. Choreography, suggested others. Something linking these bodies beyond random distribution. Atlas had not just extended the mystery, It had raised the possibility of a sequence. If the anomalies were natural, energy budgets had to explain them. Models suggested that CO2-driven jets could, in theory, produce thrust sufficient to alter a comet's trajectory. But the orientation of Atlas's acceleration did not align with observed outgassing. Some proposed that subsurface cryovolcanic fractures released gas in unpredictable bursts, a mechanism resembling geysers more than jets. Measurements of gas and dust output implied an energy release equivalent to several megatons of TNT per day, enough to move the body slightly, but not enough to account fully for the observed path. That mismatch drew attention to secondary effects. Could cosmic ray weathering have created a hardened crust, focusing pressure in odd directions? Could shielding layers allow certain compounds to erupt asymmetrically, producing the illusion of controlled pulses? Other researchers noted the rhythmic modulation in its light curve, the so-called thermal heartbeat. If natural, this might be a cycle of stress fractures, opening and resealing, a quasi-periodic breathing. But if engineered, always labeled carefully as hypothesis, it could resemble a regulated exhaust, a system designed to balance thrust without breaking the nucleus apart. The split was sharp but contained. Officially, the explanations lean toward unusual but plausible physics. Unofficially, in conference corridors and late-night discussions, Atlas had become a case study in how little we understand interstellar debris, and how much of that ignorance could be hiding under the label anomaly. As Atlas moved deeper into its inbound arc, a coordinated global campaign mobilized. The James Webb Space Telescope locked onto the coma, dissecting its infrared spectrum night after night. The Very Large Telescope in Chile tuned its ultraviolet spectrograph to track faint emission lines, while ALMA scanned for millimeter-wave signatures of exotic volatiles. Hubble added optical imaging, its sharp focus mapping tail evolution in detail. Even TESS, designed for exoplanet hunting, was repurposed for photometry, charting light curve variations that hinted at rotational instability. On Earth, the Rubin Observatory devoted emergency survey time, capturing wide-field sweeps that mapped dust trails and potential fragments. Data moved quickly across agencies, an unusual level of scheduling flexibility for a comet, more akin to how near-Earth threats are handled than routine science. Citizen astronomers contributed too. Small backyard telescopes logged sudden flares, some brightening events doubling Atlas's output in hours. These grassroots reports fed into professional pipelines, often providing the earliest alerts for outbursts that larger instruments confirmed later. For visual analysts, overlays piled up, spectral spikes rising and falling, tail disconnection events traced in blue and red, trajectory diagrams with residuals highlighted in neon. Atlas was now the most intensely scrutinized interstellar body in history, and still refusing to conform. Then came a pause that few expected. For nearly 2 days, several public data archives displayed errors or incomplete records for Atlas observations. Light curve files vanished into unavailable tags, while spectral logs returned placeholder text. To most, this appeared as routine server downtime, but in the online communities following Atlas closely, the absence was noticed. Speculation surged. Had the anomalies intensified during the blackout window? Was something discovered that required verification before release? Threads filled with conjecture, some claiming deliberate suppression, others suggesting technical glitches. NASA's official voice stayed measured. Press releases emphasized calibration, noting that high data volume instruments like JWST and Rubin often undergo temporary lockouts while files are validated. Yet the timing, falling immediately after another burst of unexplained acceleration, fed suspicion that the full picture was being managed. Harvard and other academic centers maintained silence, releasing only pre-scheduled abstracts. No new spectra, no fresh light curves, just a quiet pause in the flow of updates that had been near daily. Clear disclaimers are needed. There is no proof of intentional withholding. Such delays are common in astrophysics. But the optics were undeniable. In the vacuum of official communication, public imagination filled the gap. Atlas was now not only a scientific anomaly, but a cultural one. Despite its mysteries, Atlas remains visible to anyone willing to look. For observers in the northern hemisphere, binoculars will reveal it as a faint smudge across the constellation Pegasus through late 2025. As it nears perihelion, predictions suggest it could brighten into naked-eye visibility, rivaling the brighter comets of recent decades. For those with small telescopes, the real spectacle lies in the tail. Reports already note rapid changes, jets reshaping the fan-like plume, dust streams splitting into separate strands. Capturing even a few minutes of footage can contribute valuable data on its evolving morphology. Professional networks encourage amateurs to report their findings. The Minor Planet Center accepts positional data, while the American Association of Variable Star Observers hosts campaigns for photometric monitoring. Even simple brightness estimates help refine models. The global campaign has shown that vigilance is not confined to the world's largest telescopes. In many cases, citizen alerts were the first warnings of flares, later confirmed by professional facilities. Atlas has become a shared mystery, one that anyone with clear skies and curiosity can join. So while NASA and Harvard wrestle with theory, the night sky offers an open invitation. Watch closely, record carefully, and be part of the unfolding puzzle. Atlas now stands as a paradox, chemically inverted, accelerating beyond expected models, spinning with a strange thermal heartbeat, and framed by a blackout window that left its most crucial hours unseen. NASA's official reports emphasize calibration. Harvard's memos explore exotic but natural possibilities. Yet the core fact remains. The anomalies stack higher than explanations. 3 interstellar visitors, 3 deviations from the norm. Oumuamua with its silent acceleration, Borisov with its volatile overload, and now Atlas, fusing both into something stranger still. The odds of encountering 3 anomalies in a row in the very first 3 detections border on impossible. The stakes extend beyond curiosity. Interstellar objects are not just scientific prizes. They are test cases for how humanity interprets the unknown, for how planetary defense adapts when the rules break down. If Atlas is simply an extreme outlier, it forces new models of chemistry and physics. If it is more, an echo of design, as some carefully whisper, then the implications shift from academic to civilizational. For now, the verdict is suspended: coincidence or choreography, built or born. The question lingers, unresolved, as Atlas continues its flight. And if a 4th visitor arrives with similar anomalies, the debate will move from speculation to pattern. Subscribe for updates because the sky may not be finished with its surprises.